Hello everyone and welcome to the demonstration of the Work-Energy Theorem. Sorry for taking so long uploading this video, but here we are. Okay, in order for this proof to work out, I first need some background, a little background. It doesn't take us too long. Okay, and this background is about the notation delta in mathematics and physics. So how does this notation work? I'm going to give you a very quick example. Suppose you have a kid, 1 year old, and then this kid's gonna grow a little by 2 years old, right? So in here we say that this kid has an initial height, and after 1 year he's gonna have a final height. Okay, let's say that the initial height is, I don't know, 0.7 meters. Is that good for a 1 year old? I don't know, I don't care. And then after 1 year he has grown up to 0.8 meters. Okay, so let's see how I can write this change in height in mathematics or mathematically. What I can do is this. I can use this notation to say the following. The change in height is defined as the following. The final height minus the initial height. Okay, this is a definition. And what that means is the following, that the change in height is equal to the final height, which was 0.8 meters, minus the initial height, which was 0.7 meters, and that gives me a change in height of 0.1 meter over a period of 1 year. Okay, so that's how we use this notation, this letter. It's called delta. It's a Greek letter, and we use it in this way in order to express change. Uh, when I write this, delta v, or change in velocity, all I'm saying is a final velocity minus an initial velocity. That is a change in velocity. And I can use it for so many other things. The change in my um, the change in my balance account, okay, which is my final balance minus my initial balance if you have a bank account, and so on. So it basically it works in the same way for every quantity that you put in here. Okay, it's the final quantity of this one minus the initial quantity also of this one, and that's how this notation works. So keep that in mind. Okay, now let's go on to the proof. In order for this proof also to work better, I need you to do this. I need you to suppose that you haven't heard about kinetic energy. Okay, suppose we haven't told you about what this thing is. You don't know. Let's just forget for a moment that you know what this is. Okay, so let's start. How do we prove the work energy theorem? We do it in this way. We can do it in this way. I'm gonna place a particle here, and I'm gonna do an experiment on this particle. I'm gonna apply a force in this direction, and so the particle will have a displacement also in that direction. Okay, we have two vectors and they are parallel. So as you may remember, the work done by the force on this particle is defined as the force times the displacement times the cosine of the angle between the force and the displacement. Now in this case, since the vectors are parallel, the angle between them is 0, and the cosine of 0 is 1. So the work done by the force simplifies to this equation. Okay, and let's keep this for a moment. That was the first step in the proof, doing this mathematical work. Good. Second, I'm going to ask myself the following question. What is the effect of a force doing work on a particle. What's going to happen if a force F does work on a particle? What's going to happen to this particle when this force does work on it? Let's answer that question. Now, the way in which I'm going to answer is going to sound extremely weird at first, but just bear with me, okay? You're going to understand at the end what I'm doing. I hope so. So let's start this way. I'm going to write this equation. This is a classic kinematics equation, which is the final velocity of a particle to the square equals the initial velocity of the particle to the square plus 2 times its acceleration times its displacement. You can look up this equation in any standard physics book. And next, what I'm going to do for the next probably 4 or 5 steps is going to do some algebraical manipulation, okay? And it goes like this. First, I'm gonna do this. Okay, try to understand each step, what I'm doing. Okay, so from this point to this point in the manipulation, all I did was subtracting vi squared in both sides. I'm gonna do little steps every single time. Now I'm gonna divide both sides of the previous equation by 2, and I'm gonna get this. Next, when you have an addition or a subtraction like this, all of that divided over a number, you can separate such subtraction in this way. The first number over 2 minus the second number over 2. As you can see, I'm taking small steps. Okay, now this number divided over 2 can also be written in this way: 1/2 multiplied by such number. And the same can be done here. Perfect. Next, I'm gonna do a weird step that you may think like, why is he doing that? But the real question in mathematics is this: is it valid? Is what I'm doing valid? And as long as you can answer that question in the positive way, then the process is allowed. So what I'm gonna do is this: I'm gonna multiply both sides of this equation by the mass of this particle. So can I multiply both sides of this equation by a number, by the mass? Sure, why not? That's a mathematical valid step. So I'm gonna do it. I'm gonna multiply both sides of this equation by the mass of this particle, which I'm calling obviously m. Perfect. Now, let's take a little pause in here and tell me, what does this mean in physics when we multiply the mass times acceleration? What is that? According to Newton's second law, this is clearly the force, right? So I'm gonna put that in my equation. As you can see, I'm taking very small steps. This is the way that mathematics should be done in order to be understood, very little by little. Okay, now look at all of these, guys. Look at this. What is this? Force times displacement. Look at this. Oh, we have it right here. It's nothing but the work done by the force, right? Look. So I can write this as the work done by the force, which I'm gonna do. Perfect. We are very close to the end. Now I'm gonna flip, look at this equation, and I'm gonna flip the sides. I'm just gonna rewrite it in this way, which is obviously the same. Okay, now again, let's make a small pause right here, and I want you to look at this final equation. We are 2 steps from the end. Look at this quantity and look at this quantity. Look at them closely. We have 1/2 times the mass times the final velocity squared minus 1/2 times the mass times initial velocity squared. Aren't these two things the same? They are, right? They are the same quantity. 1/2 times mass times times a velocity to the square, and the same here. The only difference is these subindexes, final and initial. Okay, but they are in fact the same quantity, only that at a final point in time and at an initial point in time. So at this point is where the physicist decides to do the following, and this is a very common thing in science, extremely common. Those of you who are going to go into engineering or science or medicine, etc., economics and so on, a very common thing in science is the relabeling of a quantity. Okay, the relabeling or the baptizing, el bautizo of a quantity, in order to make it easier to understand or easier to write down. So at this point, some physicists a lot of time ago decided to call this quantity, which I'm going to do in here, this quantity 1/2 times the mass times the velocity squared of a particle. They decided to call it the kinetic energy of that particle. Okay, they're just giving a name to this quantity. Any other name would have worked. Don't think that this name has a special relevance. Okay, any other name would have worked. So I'm calling all of this K, the kinetic energy. And with this little creation of the mind, what I can do next is rewrite this equation in this way. Okay? Can you see why? Because all of this is the kinetic energy, but final because of this subindex. Look at this. Look at this and look at this. This is the kinetic energy, final, or the final kinetic energy, which I'm writing right here. And this is the initial kinetic energy, which I'm writing right here. And if you remember from the background that I gave you at the beginning of this video, when we have a change in a quantity in this way, the final quantity minus the initial quantity, we can write this as the change in such quantity. So in this case, it will be the change in kinetic energy. And we are done. Look at this, guys. We have proven that when a force does work on a particle, it's gonna change its kinetic energy. And what is the kinetic energy? It's this quantity, this particular quantity of the particle, 1/2 times its mass times its velocity squared. Okay, and that's the end of the proof. We are done. So if you understood maybe 60 or 70 or 80% of this proof, congratulations. Okay, or see it as many times as you want. Do the same steps that I'm doing. Okay, that's a very good exercise if you're going into engineering or science, if you're really interested in this type of things. And don't worry too much if you don't understand it completely. I believe that knowledge happens in stages, and you may understand something with some degree of precision, and later on in life you will understand it fully. I guarantee that to you. I remember a time in which I could follow this proof, but I didn't understand it completely. But now I do. Okay, so the degree of precision in knowledge grows in your mind. So that's it, guys. I hope you have enjoyed the proof, and thank you.